Okay, we can get started. Today, I want to finish the chapters 1 and 2 that we were discussing in the last lecture. You should have the homework assignment and the homework project. The first homework project, it's similar to the one we had last year too. Essentially, you should install a Linux operating system in the lab machines. I gave you the code to enter the room. It's printed, and you should all have accounts. And to get super user, you should do sudo. You should all have ways to become a super user administrator, right? So if you do, right, it'll ask for your password, and once you have that, you're a super user, you're administrator. You can do whatever you want on that machine, right? And the password is your NerdM password. But the machine is not your AFS or whatever. So the space you have is unique to that lab. It's not backed up, so don't store anything important in there, right? But you should have enough space for you to work on projects, because your course, your AFS space probably does not have enough quota to compile kernels and stuff, right? And if you run into, so as with all these programming projects, start early, and if you run into any troubles, send an email to the class, and they can take it to that, right? So the idea here is not to, it may be easy for some of you who's done that, but I want everybody to go through the process of building the kernel to kind of see the different components that are in play. When you watch the compilation, you kind of see what's going on. And as we go through the course, hopefully it will be more clearer, right? So it'll be more helpful, right? Does that make sense? Right. I'll let you think about it, and if you have any questions, you can drop me a note, or we can discuss more in the next lecture, right? Yeah?
Quick question. On this page with the individual homework, the due date says Monday, January 39th.
Yeah, I think it's not 39, it's
29.
Probably. On the lecture schedule, it gives the right date. I'm sorry, I mean, it's probably not 39, right? Probably not 39, and probably not around, modulo 31 either, right?
Professor, do you have any more copies of the project?
Was there any more project copies hanging around? There are more homework assignments than projects, even though I printed the same amount of copies. So it's somewhere here. If not, it's online in the PDF, so you can download it, right? So going back to we're still looking at the overview of what operating systems are, trying to get a grasp of what it does, how we interact and stuff. And when we left last class, we were talking about system calls as a way to interact from the user space to the kernel space, and kernel being the core operating system, right? So one of the issues we have to worry about is inside the kernel, you're privileged, you're allowed to do whatever with the machine. Outside, as a user, you're not allowed to do certain things. For example, you're not allowed to change other processes. We haven't seen what processes are, but the control function, you're not allowed to change, right? If the kernel decides that you as a PowerPoint slide should get the screen, right, your IE should not be allowed to go and muck with that, right? So for those stuff has to happen in the privileged mode, and that's why you have to go to a system call, right? Like manipulating the hard drive, formatting the hard disk, right? It cannot be just given to everybody, because then what prevents you from formatting it or doing something bad with it? So the way there are a lot of abstractions from what you're used to as a programmer and what really happens. And many of you seem to have been using printf or scanf, which is actually a C library, right? So first you write a program in a C library or some other library that you can think of, and then from the library you have to translate to a system call like read, right? Which is basically defined by POSIX standard, right? Once you define that, you have to translate that to a Linux specific system call, right? And Linux has around 322 system calls. So it has a lot more system calls than what POSIX allows you to have. And it gives you a lot more finer grained error messages than what POSIX give, because POSIX essentially is so you can write a C program using read and write on Windows or Linux or Mac and it still works, right? But when you translate to the lower level machine, it's specific to the version of Linux or OS or whatever, right? So you do the translation to the appropriate kernel system call, right? And then you call inside the kernel. So the way you call inside the kernel is you have the notion of system call numbers. You figure out what the number for the particular call is. You store it in some known location. You put all the parameters, all the stuff that you're passing into the function in some known location, right? Then you do a trap. And trap is a mechanism for you to do a software interrupt into the kernel to say, I want to execute a system call. So the kernel does some sanity checks, make sure that you're doing the right thing. And then it'll, based on the call number, it figures out what function to run and gives it all the parameters, right? And then you proceed and do the functions. Yes?
So a trap is what sends from the...
Yes.
So the trap sends it to the kernel?
Yeah, trap sends you from the user to the kernel. Essentially trap would do a software interrupt into the kernel, and the kernel, when it's ready, will come around and continue. So when you do a trap, you don't just go into the kernel. You tell the kernel, I need to get in, right? You do a software interrupt. So the kernel is doing something hardware based. It won't talk to you. It'll make you wait, and when it's ready. So we'll see a little bit of why these things are happening, but the kernel data structures are important, right? If the kernel is doing something, you don't want to mess with it, right? And one of the data structures that kernel uses a lot, which you'll use in a programming class, is either arrays or structures, right? So or linked list structures, right? So when it's manipulating the linked list structure, when it's like changing some field halfway through, or if it's changing some tables halfway through, it won't talk to you. It'll finish all the stuff it has to do, because if it leaves something hanging, your machine will crash, right? So it'll finish all the stuff, and then it'll take you and then do this stuff, right? And when it returns error message which makes sense for the particular operating system. And then your wrapper code would change that into something which is defined by POSIX, right? So if it says, so it may return specific messages depending on whether it's a hard disk or a CD or what have you. But POSIX gives you only a few error messages, right? Is that clear? This is where we left off in the last class, right? So if you think about it, it's not trivial. All the things which has to happen is not trivial, right? So if you want to make a system call, I have to figure out what the number is, which is easier. Copy all the parameters into this space. Do a trap. Wait for the kernel to get ready. Take me up, right? Do the switch from normal user to administrative user, and perform these operations and get back. So there's a lot of overhead involved with doing this. So it's not a cheap operation, right? So when you write a suppose you're writing a C program, right? Call plus, right? Obviously, you won't do something like this because it doesn't have any effect on the stuff, right? Because it's not getting passed. But if you have something very small like this in a C program, right? It's okay because the overhead of calling a function is not that high. But if you wrote a system call which is like this trivial, right? When it comes here, you have to figure out you have to do all this stuff. You have to figure out what the system call number is, store this I somewhere, you do a trap, right? And then you have to switch from user to the kernel mode, right? And then you do this stuff, and then you have to switch back from the user kernel to the user mode and all those things, right? So the bottom line is system calls are expensive. So you don't want to do a system call unless you have to, right? You only do it when you absolutely need something from the kernel that only the kernel can give you, right? If you want to manipulate the hardware, you have to go to the kernel. But you don't want to implement something like increment I inside the kernel, because if you do, the performance cost is very high, right? And we'll see in a couple of slides why you would what's the trade-off that I'm talking about. But essentially, the system calls are not cheap. It takes a while, right? And when you talk about hardware, whenever you do the context switch, right, within the hardware community, you have to flush caches, you have to flush all the buffers because you're going from normal to a system user, right? So there's also hidden costs in terms of flushing buffers and other hardware costs in switching. So you don't want to do that unless you have to, right? And we're still talking about other stuff which makes up operating system. And there are other stuff like systems programs, and this is the difference between operating system and a kernel, right? These are functions which are there, which without them your machine is completely useless. You have to have a shell or some kind of a GUI for it to interact, right? You don't just have the operating system, you have this other stuff. Then once you log in, you have to have some way to look at the directory, do the login and all those things. Those are called system programs. They're fundamental to the way the system operates, but they're no more privileged. They're not anything special. I mean, somebody wrote this because these are important for every user, but they have no more privilege than for the kernel, right? The kernel maintains all the hardware and all those things, whereas these are goodies which are good, but nothing special about them, right? Yeah. Do you have a question? Oh, sorry. And there's a lot of argument about what goes here, right? There are some things which seem obvious, like the way to log into a machine seems obvious, right? And if any of you remember, a few years back, Microsoft was, going through an antitrust lawsuit, essentially defining Internet Explorer as part of the operating system, right? So there's legal ramifications of what you define as a systems program, but for the most part, these are not special. These are interesting, nice utilities, right? And when people define operating systems, some of the things that they want to define, they have to figure out what kind of users they are targeting, and that's not an easy task, right? So companies spend a lot of money trying to figure out who's the target audience. So they're going to build a desktop. They have to figure out who's the target, and then make choices based on what this particular user would be doing. And if you're going to do a web server, you know what kind of web server you are, and you kind of do those things, right? And the design principle when you're designing new operating system is the notion of separating the policy from mechanism, right? Policy defines what should be done, and mechanism will define how you will do it, right? So if you think of the read call we talked about before, policy would say, when I say read 10, I want the next 10 bytes, right? Mechanism would figure out if it's a hard disk, something has to move so I can read the stuff. If it's a CD, then something has to rotate and I need to read the stuff. If it's a flash, whatever specific mechanism I have, it has to figure out something. But the policy says, my goal is to read some bytes, right? The mechanism is the how you do it. If you separate these two, and if you're careful on what the two things are, it makes life a lot easier, right? You define, you make system, you make changes to the system using policy, and you don't worry about the mechanism, right? And that's the thing which makes you write a program on Linux and take it to Windows and sort of work for the most part, because you're defining the policy, not the specific mechanism, right? It also allows like Microsoft to make the things faster. So if you have a read on Windows XP, they could change the mechanism in Windows Vista to make the things go faster, because you define what you wanted and it's doing the underlying stuff, right? So this is a design philosophy that kind of permeates inside the operating system, and that should be, it'll become more and more obvious as the developers develop something. So if they make a small change in Windows XP, right, when they move over to Vista, right? I forget how many Windows users are out there, right? Anyone want to make a guess on how many Windows XP users are out there throughout the world? Tens of millions, right? So you're making changes in the mechanism which potentially affects all these people, right? There may be subtle interactions in how you do read, that the mechanism that you read, which moved from the old operating system to the new operating system, which may affect a whole bunch of people, right? So if you implemented the policy right, and the mechanism, you can fix it, right? If the policy is broken, then you're kind of stuck, right? So making a change like for something like Microsoft, it's a big endeavor, because they have to make sure that whatever they change still works, right? How many of you use or seen Windows Vista? How do you guys get access to that stuff? They're not selling it yet, right?
I worked for Lockheed this past summer, and they gave me a copy of the beta version.
Okay. Is that how you got?
He's my roommate.
Okay. Okay. Yeah. So when they have to make a change like that, when they want to go to a Vista, they would like things to be new, but they don't want things to break, right? So they want to change the mechanisms to make stuff faster or whatever, while still maintaining the policy of what they're supposed to do, right? So in terms of how you build the operating system, there's a number of different ways of how you develop operating systems, right? And the main ways are simple, layered, and microkernel and modular. And we'll see what those are, right? Simple is the MS DOS, and I think few of you said you really use the DOS operating system, right? This is not the DOS which you get from Windows XP when you do command. This is the real deal, right? And so basically, what we can say is you can't say anything there. I mean, how many of you use the DOS? So what comes to your mind when you think of DOS?
Command line backslashes.
Backslashes? Have you ever written programs for it? I'm sorry?
DIR, not LS.
Yeah. But has anyone played with TSR, terminate, stay resident stuff? So basically what it does is, DOS is the ultimate operating system if you want to do something with it, if you want to hack it, right? Because practically it doesn't enforce anything. It's not an operating system, right? All the things we're going to say in this class, it doesn't do. It doesn't do protection. You want to trash somebody else's program, go right ahead, right? You want to write into kernel, go right ahead, right? So you have these programs called TSRs where you write this program, it's like a virus, it attaches to the machine, right? And people put like time and stuff on the screen, right? So basically, so if you look at a DOS screen, right? You can write a little TSR which puts the current time here all the time, right? And you can put my name here all the time, right? Which will stay regardless of what application you run. Basically, you go into the kernel, and wherever it's writing into that buffer, you keep writing, right? So there's no protection. You can do whatever you want, right? It's great to write games in that machine, because practically you have the machine. There's not much service. You have some sort of a device drivers and stuff, but you're free to ignore anything you choose, right? So you get the ultimate performance because nothing stays in your way, right? If you run a DOS game, it basically takes over the machine. When it exits the program, you have to reboot the machine because it completely takes over, right? So in that sense, it's great because it takes over the machine. But for everything else, it's a nightmare, right? Because if you wrote a program and if the program was corrupting some memory, you will have some strange things because you could be corrupting your own caches, your own buffers. You can do whatever you want, right? So it's simple because it practically doesn't do anything. It's the fastest because it doesn't do anything. It's the unsafest because it doesn't do anything, right? So this is sort of the thing. So you have the device drivers and stuff, but as you can see, the applications can directly talk to the BIOS, and everything can talk directly to anything. So spaghetti code, and thankfully we are moved past that, right? So the other approach is a layered approach where you don't want, so the thing I was talking about before, so you kind of have something like a kernel and the user space, right? You kind of have a layer like this where this is more privileged than something here, right? And nothing prevents you from having two layers. You can have as many layers as you want. In fact, the immediate parent of Unix, which is Multics, Unix came from Multics operating system, had many layers. It had a ring structure, right, where it's like an onion peel, right? So the outermost has the least privileges, and as you go inward, you get more privileges, right? And Unix uses only two. So if you think of that, it's sort of, this is the kernel and this is the user, right? Whereas in Multics, you'll have many circles like that, right? So essentially, as you move inward, you get more privileges. As you move outward, you lose privileges. And doing this is, making it this way, it's more modular, because now you have to make sure that stuff which needs more privileges should be inside, and stuff which doesn't need that much privileges should be outside. So you have to, so you can enforce some of the protection and stuff we'll read in this class, right? So these machines are much more stable than what the simple operating systems, and to a large extent Windows XP follows something similar, right? The only problem is you have to keep going into the kernel to get your services, and you have to pay the overhead I mentioned. Every time you cross these boundaries, you pay some overhead, right? So that is one problem. The other, so the nice thing is it's clean. Most of your Windows are on Mac or Linux operate on something like this model, right? It's clean. The one problem that people don't like about this approach is whatever goes inside the kernel, you have no control over, right? So if you buy Vista and the Vista does something certain way, right? Maybe it's using the CD in a certain way. It's running the CD really fast, right? And if there's a reason why I want to change that to make it run slower, I, as a normal user or programmer or what have you, can't do anything because it goes inside the kernel, right? So if I want to make that change, I either have to talk to Microsoft, right? I'm sure there's millions of people talking to Microsoft, or I join Microsoft and make this happen inside their building, right? So that may be good, that may be bad, right? It's good because that means that Microsoft's argument would be, we know best. We know what our operating system is. So we know what's best, so you should live with it, right? And your argument could be, yes, you know what's best for your 40 million users, but that's not good for me, right? So there's a big debate whether what's good for everybody, it's good for you, right? So there are other ways people looked at other ways of doing this because this is good for leaving all the control to Microsoft. It's bad in the case where somebody else wants to make a change, right? So in terms of, if you look at the Unix structure at a very high level, right? What's inside the gray box is what you typically call the kernel, and that, which is what we'll read about in this class, right? The interface to the bottom is essentially the interface to the different device controllers, so to the disk controller or terminal controller or what have you. It's very specific to that particular hardware, right? So it's very machine mechanism dependent, right? If you have to talk to a laser printer, you talk a different language than if you're talking to a dot matrix printer or a screen or what have you, right? So each of those is very specific. So this is what you get by drivers. When you buy a new machine, some hardware, you get a driver essentially which lets the kernel talk to that particular machine, right? And we probably won't spend too much time on that because it's specific to that particular hardware, right? What we're going to spend time is on how the kernel manages whatever hardware it has, right? Which is inside the gray box. And on top, you have all the system libraries like login and what have you, right? So going back to the let's go back to the Unix model, right? So you have the kernel and you have the user, right? So everything inside here is done by a vendor and you are here, right? So you have really no control. So, and over the years, the vendors keep adding stuff into here, right? I think Microsoft operating system right now is like 50 million lines of code or what have you, right? So this gets bigger and bigger and bigger and bigger. So it gets like people call bloated, right? So what you want to do is do this separation again. Do the mechanisms inside and move the policy up here, right? What we talked about, right? So for example, the mechanism is I want to create a new process, right? We haven't seen what process is, but let's say I want to create a new process. I want to use a disk or something, right? Put the mechanisms here and how to use it, how to allocate everything, move it into the user space, right? And that's the notion of the microkernel. Microkernel where you say, I keep the same notion here, except I make this much smaller. So if you thought of somehow this space meant something, right? Somehow this, volume something. When you say microkernel, you say I move it here, right? I remove the stuff here. I move all the policies which used to be in the operating system up here, and only the mechanisms stay inside this small, hopefully micro, right? And since this is small, it's easy to debug. It's stable. You never have to change this. That's the idea, right? So you have this stuff. It's extremely clean. It stays there forever. You implement different policies, right? So one of the easiest way you can think of different policy is when so the newer Mac operating systems runs on the same hardware as Vista, right? So you could potentially have a Mac process manager and a Windows process manager, right? If you design this stuff right, you will have one here which does process. That's right. Right? You have something inside your microkernel now, right? You move the specifics of how Macintosh does it outside. You may move the specifics of how Windows does it outside. You can potentially have more of these, right? So that way, you have this extremely fast, extremely simple core, and you can change them the way you want, right? You can in the same machine make it run like Mac. You can make it run like Windows, right? Or if, for example, for your particular application, you don't need the process at all, you can just remove the whole thing, right? So you can customize your operating system to be precisely what you want, and that's the argument for microkernel. You want such that people are fed up with Microsoft Vista being so huge. If it takes 50 million code, who believes that Microsoft actually knows what's happening, right? I mean, it's kind of hard to imagine that some human being inside Microsoft knows precisely what's happening within this 50 million lines of code. How many of you spend time in Microsoft in summer internships or what have you? Wow. Okay. So one of the fascinating things about working in Microsoft or stuff. I knew a guy who has a PhD who was a part of a group which was worried about how the control panel looks, right? How the control panel looks, including the icons and how it looks, right? The catchphrase is, that sounds awfully boring, right? Your whole life with a whole bunch of you, day in, day out, you go in and go out, and how many of you remember the control panel interface, right? You've probably seen that, right? I don't think you sat there and marveled that, I don't think you sat down for half an hour and looked at stuff. That is a piece of art, right? No, I mean, you're usually going there to change something. You're changing some device driver, some parameter, right? So you're just going there. But that person sits there, their goal is to make it look nice, right? And he's a part of a group which does that, right? So the point is, it's gone to such a large extent that human being possibly can't know what happens within the process management or something. So it's so humongous. 50 million lines of code is a lot, right? So if you get rid of this and you make this small, right? We don't know what small is, but let's say it's like 10,000 lines, right? Then enough people know precisely what it does. They know exactly there should be no bugs. All the bugs should happen at this layer, right? In some sense, your Windows XP is a microkernel. There are no longer operating systems which are precisely one over the other, right? Within your Windows XP, there's a hardware abstraction layer called HAL. We'll see that later. But essentially, they define a notion called HAL, hardware abstraction layer, and they build their kernel on top, right? So this talks to the hardware, and this provides some of the basics that they need, right? So in some rudimentary sense, Windows XP is a microkernel-based system, because around like 5 or 6 years back, Windows NT used to run on DEC Alpha and other processors, right? So they have the inerts to make it work on different processors. So it is sort of like microkernel based, right? Your Macintosh OS is microkernel based, right? The way your Mac OS X works is this part is operating system called Mach. It came out of CMU in the late 80s and early 90s kind of stuff, right? So on top of here, they have FreeBSD core, right? And over here they have Mac OS X, right? Something like this, and essentially those are run as Mark schedulable, the bubbles I talked about, right? So technically they can implement Windows like API on top of Mac by building the policy on top of it, right? So Mac OS X is a good example. So when people say Mac runs Unix, right? If you see the Apple advertisement saying that Mac OS X runs it has Unix underneath, right? It doesn't have Unix underneath. It has Mac underneath, right? Unix it's not underneath. It's core, right? It's just another peer rather than under it, right? But those are details, right? So that's the nice thing about it, So essentially they can change the stuff, but hopefully the Mark they haven't changed, right? And Mark, I think the Mark version 3.0 is what it was in '92, and it's still that. So unless there's some bug fixes or whatever, essentially this doesn't have to change, right? And this is the privileged part, and this is not the privileged part, right? So what's the negatives of doing this?
It would take a lot of time, or it takes more time.
Yeah, every time you do this crossing, right, you moved all the stuff here, but if it requires too much of this, and if you're doing this crossing, right, a lot, you'll pay a penalty. And this is the discussion I said we'll get back, right? System call interface is pretty expensive. In a normal Unix-based system, you only do a system call when you need something, you need a read or whatever, right? But in this system, you have to do this crossing a lot because the mechanisms are here, policy is here. So every time you have to make something, you have to get to here, and then you have to get to here, and there could be a performance loss, right? And usually there is. I mean, usually these things there's an overhead. And you have to develop more complicated mechanisms to make these things go faster. But that's the flip side of it, right? And sort of, your Mac OS X, has the Mark underneath, BSD on the core, and yeah.
I was going to ask, what does BSD stand for?
Berkeley Software Distribution. So that's the history of Unix. And Unix came from was it AT&T Bell Labs. Then it was given to Berkeley, where they made it popular, right? There's a lot of children of the original Unix, but it's one of they technically use the FreeBSD for their Unix variant, right? So yet another way of dealing with operating system is a modular fashion, right? Rather than so let's go back to some people don't like the idea of microkernels, right? So going back to here, right? This is the kernel, and this is the user. And you had no way of controlling anything before, right? So other way to deal with this is to have a notion of modules, right? So essentially you load a module into the kernel, right? Then it becomes part of the kernel, right? You load this dynamically, right? And this, in Windows, it's called DLL, right? You dynamically load dynamically linked libraries, right? Dynamically it loads something, right? So whenever your OS needs some new functionality, you load this module, then essentially the OS boundary becomes that sticking part, right? So if you unload it, and then if you load it in a different library, then that becomes a part of the OS, right? So you can essentially change the OS by adding new DLLs and removing DLLs and what have you. Right?
Is that what a DLL is always used for, like interacting with the OS?
Yeah. No, DLLs can be used for others. I mean, DLLs are dynamic linking, right? So it can be linked to a user process or to kernel, right? If you're using a kernel DLL, like the drivers and stuff, right? They essentially become part of the OS. So when you boot up the machine, it comes up with this vanilla Windows, right? And then it loads the first DLL, then it becomes like this, right? So eventually your machine, after you install, so this may be the Windows XP on your laptop, and this may be the this may be my Windows laptop, right? Even though we are running, this is the Windows, this is Windows, right? Depending on the modules that I loaded, I may look different than yours, right? My functionality is different because now you have this and I have this, right? And this is a nice way to add this stuff and change this stuff. It's also a nice way to crash this stuff, right? Because now you're kind of trusting somebody to become part of here, right? The whole argument that we said this should remain with Microsoft is they know what they're doing, right? Now you bought a little keyboard and then you bought a little driver which came with it, and you added it to the kernel. So now the kernel trusts, if you think of how good the code is, it's whatever Microsoft did plus whatever your little thing you got, right? So if something crashes here, so when a kernel crashes, it's very hard to recover, right? Because kernel controls everything. So if that something messes up, usually you have to go for a blue screen of death, right? So if you downloaded some DLL which was written by somebody who had no idea what they're doing, essentially your machine is as strong as this one, right? That's one of the reasons why Windows crashes for the most part, not because something is wrong inside the kernel, but something is inside your device driver, right? You have to find the right device driver and yank it, and it's a constant battle, right? But that's the modular approach. And Linux use that a lot, and Windows use that a lot, because it's very useful to add stuff, right? So for example, if you talk about a different file system, we'll see later in the class, essentially load it as a module, and bang, you have the new functionality, right? But the cost of that is now you're trusting all these pieces to work together, and they may or may not work, right? And that's why when you kind of plug in a new printer, the whole machine crashes, because when you plug in a printer, your new printer driver gets started and things crash, right? Does that make sense? So those are the three different ways of building operating systems. And back in the 90s, there used to be a big fight about which way to go, but I think the consensus now is you mix and choose different stuff. You have microkernel a little bit, you have a little bit of monolithic, which is the layered one, and then you have a little bit of modules depending on what you do, and then you kind of move forward, right? So that's the way of organizing operating system. Now the notion of virtual machine is something that a lot of people are pushing towards, especially in utility computing kind of model. So I think it's worth looking at, right? The idea here is people. Okay, so you know that you have all these issues and you have all these crashes and stuff, right? So instead of dealing with this, if somehow, let's say this is your, right? This is the machine that you get with the OS running on top and everything, right? Somehow we can make this such that you have something here. Suppose I can make your one machine look like 3 different machines, right? What that means is so each one is completely blocked off from the other, right? Each one cannot talk to each other. They are like 3 different physical machines squished into one box, right? To talk to each other, they have to use a network. They can't just write memory or whatever. It's protected such that this machine, you have to install the new operating system. So you have to install operating system. Let's say you install XP here. Let's say you install Linux here. Let's say install BSD here, right? 3 different operating systems you install, right? And the notion of virtual machine is I create this virtual machine where it looks like a brand new machine. You install all the stuff you want here. Underneath, there is something running. There is an operating system, So this could be XP underneath here, right? But by doing this, if you mess up here, if this crashes, right, you don't bring down the whole machine, right? In the case of the kernel, when we talked about other kernels, you do something in the kernel. If you mess up the kernel, OS cannot recover because it can't do anything because it's the one which is trying to recover and it can't deal with itself being corrupted, right? Whereas here, I can crash this stuff, right? And I can you're still fine, right? If this one crashes, you lose all the stuff inside, but nothing prevents the Linux and FreeBSD to stop, right? That's notion of virtual machine. You're virtually making it look like a machine, and you're making progress, right? Now it's very resource inefficient, right? Because you have, let's say you have one CPU underneath here, right? Now this one CPU is going to be given to each one of those, right? So they may only get 1/3 of the CPU, right? So if you have a 3 gigahertz processor using crude math, each one of them may look like it's 1 gigahertz, right? And same, if you have 1 gigabyte of memory, right? Somehow you have to give it to these machines because these act like they're normal machines, right? So this could be very slow to do this stuff, right? And this is not a new concept because IBM used to do this in the 70s on their mainframe. They used to do this kind of model, whether under different operating systems. Then it fell out of favor because all their PCs didn't have enough juice, right? It's coming back up because machines are fast, right? So when you buy a dual core machine, right? I can say I'll give 1 core to the Windows XP, 1 core to the Linux, right? So I'm kind of good, right? So if I have, and Intel now has a quad core, right? So they have 4 cores, so this is like a 4 CPU, right? So we can say I'll give 1 CPU to the underlying XP, 1 to this, 1 to here, right? So I'm kind of good, and I have a lot of memory, right? The benefit here is if this machine crashes, I'm good. I mean, I start a new one, right? And that's the goal. So when you talk about utility computing is when you work with service providers and stuff, right? So a lot of the companies don't run their own servers, right? So you go talk to a company like, let's say, Amazon or Google, right? Google has, we don't know what the size is, but they build power plants to run their own data center, right? So you're talking big. So you're talking thousands of machines, right? So you have floors and floors of machines. Right? So if you want some machines, you go talk to Google and say, I need 1,000 machines for 2 days, right? You pay the money and stuff. So they want to give you all the machines for the 2 days, and then they want to take it back, right? So that's the utility computing where you don't buy the machine, maintain the machine. You just go and ask them, I want 10 machines for the day. They give it to you, right? The way they can give it to you is they can create these virtual machines, let you put whatever you want inside. You want Windows XP, fine. You want Windows XP with Service Pack 0, fine. Do whatever you want, right? They control what happens here. You don't have to trust them because you're basically running on your own little stuff, right? They package it up, and you can deploy it all over the place. You run your own application. They talk to each other, right? You don't have to trust those people, right? And when you're done, you take all the virtual machines back. Right? So it's becoming very popular, and they don't have to worry about you bringing down the machines either, because if you wrote a bad program and you crashed your machine, fine. I mean, your part went away, but your other people are running, right? So you could be sharing a machine. So Ford could be sharing a machine with GM on the same exact machine, doing different stuff. One of them crashes, the other one keeps going, and they don't even share anything. So Ford could be doing its own stuff, and GM could be doing its own stuff. They don't get to talk to each other, right? So that's the world things are going, right? It's also useful for normal computing, right? So if you bought a new Macintosh, right, there are stuff or PCs. You have companies like VMware or Parallels, which let you run this little operating system. Has anyone of you tried those virtual machines? Okay, that's an excellent way to debug your programs, right? If you're writing a new kernel, right, for the first project, you're going to develop a new kernel, right? New company-owned kernel. And you'll notice that your machine will crash often because you did something wrong, it's crashing and stuff. If you had a virtual machine, then you can do whatever. You built the wrong kernel, it doesn't boot up anymore, fine, you create a new one, right? I have the software to VMware install on the machines. I'll tell you how to do that. The only catch is it's very resource intensive, so you have to have. We can't have everyone in the class running on the same machine because there's not enough memory, right? But you can try this different stuff, right? I also have a software for software VMware, if any of you want that, right? So essentially, that's the graph you want. Instead of having this one on the left, one machine, it makes it look like there are multiple machines, right? So it's virtual, so it's not going to be creating new resources. You're sharing the resources across multiple people, but since the machines are fast, you may be okay, right? And this is sort of what I was mentioning. When you talk about data centers love this stuff because so if you have 10,000 machines you're maintaining, right? What you don't want them is the machines to be crashing. Then somebody has to go in or reboot the machines and stuff, right? especially when you're giving it out to different people and you don't know who wrote what code and stuff, right? Whereas if you do the virtual machine, then I don't have to worry about what Ford did, what GM did, because they're all inside their own little space, right? So I got this from the VMware company, right? And this is another way that they in the corporate setting that they want to use virtual machines, right? So when you in a corporation, you have lots of desktop PCs, right? And they are still managed, like even here, right? There's a desktop PC here. It's being managed by OIT, the one where I'm projecting this stuff, right? I have to trust this machine because when I log in, I may be doing some stuff that I may be downloading your grades or whatever, and I have to trust this machine, right? And the extent that I can trust this machine, it's iffy because when I leave this room, the machine is sitting here, so one of you can go in and crack this machine, right? Here, at the best, you lose is maybe your grades, which is it's not it's still important, but unlike a company where I may be making a budget which is worth like billions of dollars, and I don't want people to do this stuff, right? So what their model is, they put all whatever you're logged in your machine into a virtual machine, right? So whenever you go to a new machine, like I come into the office, I log into a machine, you download this virtual machine, and I run it in your machine, right? So I don't trust your machine at all. I run inside my own little virtual machine. So when I leave, I package it back, then I go with me, right? So the ACE package manager, and they have this little stuff. So essentially, whenever I go to a new machine, it does the management, and I don't have to trust the underlying machine, right? I do my stuff. It's all secure inside, and I move forward, right? This is something I saw from the Bushes. So if you had a chance to go to VMware, that's they're a big company, right? So within VMware, you can buy VMware. I think VMware Player you can download for free, right? You can either put it under Linux or Windows or what have you, and you can install different operating systems. And if you had a really slow machine with not a lot of memory, then this will be very slow. But on a more beefy machine, this will be fine, right? I'll very quickly talk about the other virtual machine which you probably have used is the Java, right? Java does if you remember Java, you call the Java virtual machine, right? Essentially, you have the Java interpreter running a Java virtual machine, and you can run. So your code is the same. It runs on the Java machine or the underlying machine, and it interprets all the stuff you have to do, right? And let me finish this one last thing, right? The other part that we didn't mention is the notion of how does operating system bootstrap itself and run, right? When you first get this machine, it knows nothing. It's just sitting there. How do you first load yourself, right? And you need the help of the BIOS or the bootstrap code, right? So they essentially know any machine which you buy on a Windows machine, it knows how to start up the initial code, right? So you have to first have initial code somewhere where it always knows where to look, right? So when you boot up the machine, let's say it always looks at sector 0, right? Your machine will always go to sector 0 and run whatever is in there. So if you want the operating system, you should put something in there which tells it what to do next, right? You should know how to read a disk from there, right? So it'll read that part, and then it'll read that part, right? So you go through different steps because when you started out, the machine is empty, right? All it says is, I'll go and start whatever is in here. And from there, you have to go step by step, right? And then it has to figure out what's in the machine. So if you look at as part of your project, when you look at the stuff, right, it'll go and tell you that, okay, it's checking to see what hardware it has, what drive it has, what network it has and stuff, right? And some of your projects will fail in this part because if it doesn't know how to read the right thing, it has to crash. If it doesn't know how to read your hard drive, there's nothing else it can do, right? So that's one of the places you will fail. If it doesn't know how to read your network card or hard disk or whatever, and that's one of the things that hopefully you'll learn from doing this exercise, right? And that's it, and we'll continue with the processes on Wednesday.